Welcome to the next video in Discrete Mathematics. This is video 4, where we will discuss cutting the plane with v's this time. This corresponds to Chapter 1, Section 2 of the textbook. So this time, rather than cutting the plane with straight lines, we'll consider cutting the plane with these sort of V-shapes. Now you can see, and it I think makes intuitive sense, that if you had just a single V-shape or an angle, then you would, just like with a single straight line, cut the entire plane into two different regions. But this time, if you had two V-shapes, then you could try to get, again, sort of the maximum number of intersections, the logic of that being very similar to straight lines. But this time you get 7 regions. And when you think about the logic of how many regions you can possibly get from a given n number of V-shapes, it makes sense that, well, a single V kind of looks like just two intersecting lines where we merge some two of the regions, right? Because we do not actually extend the line out past this point of intersection, then you can kind of imagine that these two regions that you would have gotten from if you had two separate lines, those two regions are kind of merged into the third region, right? So you can almost imagine this region here that is, sort of separated out. Well, that's still there. But while these two regions used to be separated, they're now merged together with this third one, this green one, let's say. And then if you draw the picture for two intersecting V-shapes, so one here, and again, you can kind of imagine that there's some region that would have been separated if you had 4 lines, right? And what you can see in my diagram here is that in blue, I've drawn all the regions you would have gotten if we extended these V-shapes into complete lines. And so again, this green region is one of the regions that you would have gotten in that sort of old regime. But now we're taking these two regions and merging them into it. And then also over here, sort of due to this intersection, we get another 2 regions that merge into the sort of shared region of that green area. And in general, every single time that you add another V, you are effectively getting the same thing as having twice as many. So you can kind of see it illustrated here and here in these two specific cases. You're getting the same thing as if you had twice as many lines, right? So for n V's, it's like having 2 n lines. But every single, right, for each n, for each time that you do this, you lose, right, 2 of the regions get merged into some other existing region. So, so here you would get 2 times 1, here you would get 2 times 2. And from this perspective, we reason that Vn is equal to exactly what you would get from doing straight lines, right? By the way, I'm using Vn. I think it's probably clear, but I'm using Vn for the number of regions that you get with n V-shapes. And I'll use L to talk about the number of regions that you would get from a given collection of lines. And so for any given V-shapes, you get the same thing as if you had twice as many lines, except that because every single time you do this, you merge 2 regions into some other existing region, so you lose 2 regions. And so every time you do this, right, that's n counts how many times you do this, so you lose 2n regions. Well, we already found in a previous video that the formula for the number of lines is given by this right here, this formula. And so there we have it, right? This, right, when you put it all together like that, well, now we have a closed form for the number of regions corresponding to V-shapes. If you appreciated this content, please like and subscribe. And if there's anything that we discussed here where you'd like to see it elaborated further, I might be able to answer questions in the comments, or for substantial topics, I might make an entire video and add it to the playlist.